Hey there, deep divers. Ready to get a little lost?
Only to find our way out again, right?
Exactly. Today's deep dive is all about the depth-first search algorithm.
It's a powerful tool for exploring and, well, solving all sorts of problems in computer science.
And to guide us through this deep dive, we have some really cool notes on DFS algorithms.
Originally written in Chinese, actually.
Yeah, we've translated them for you so we can unpack all the exciting ways that DFS can be used, like how to find all possible combinations of numbers.
Or generate unique permutations.
Even solve word searches. It's a real problem-solving chameleon.
You know what's really fascinating about DFS? The underlying logic is pretty universal.
You mean like a master key?
Exactly. You can apply it to so many different scenarios. It's like having this master key that unlocks all these different puzzles.
Okay, so before we unlock those puzzles, can we make sure we're all on the same page? Like imagine you're in a maze.
Okay, I'm in a maze.
You'd probably pick a path and just keep going as far as you could before you had to like turn back, right?
Yeah, makes sense.
That's the essence of depth-first search. It dives deep into one branch of the problem before backtracking to explore other possibilities.
Now, before you even jump into the code, there are 3 key questions you need to consider.
Oh, okay, like a checklist.
Exactly. First, how do you define the function and its parameters to represent the problem? What information does your DFS function actually need?
Got it. So we're setting up the tools, right?
Exactly. Then you need to think about how to break down the problem recursively. How do you divide it into smaller pieces?
So we're creating a set of instructions that the algorithm will follow again and again, diving deeper each time.
Right. And that brings us to the third question, which is super important, the exit condition.
The exit condition.
You need to tell your algorithm when to stop recursing. Otherwise, it'll just keep going forever.
Like someone lost in a maze.
Yeah, exactly. Define the function, braid it down recursively, and tell it when to stop.
Okay, I'm starting to feel like a DFS pro already. Can we see this in action?
Absolutely. Our notes actually start with a classic problem, finding all the subsets of a given set of numbers.
Subsets, like from math class.
Exactly.
Mm-hmm.
But how does DFS handle all the potential combinations? It can be a lot.
Yeah, I can get out of hand pretty quickly.
Right. Well, it actually does it quite elegantly by systematically exploring all possible arrangements.
Oh, okay.
The code in our notes defines this DFS function that basically recursively adds a number to a potential subset, explores further, then remove that number and tries a different one.
So it's like trying every door in the maze until you find all the hidden rooms.
Precisely.
So why is this systematic exploration so important? Like, could we miss some subsets if we didn't do it this way?
That's a great question. By going through every possible combination, DFS makes sure that we find all the subsets without missing any.
It's thorough and efficient.
Yeah.
Okay, I'm starting to see the power of this methodical approach. What about problem 77? Finding combinations of a specific size, is that similar?
It builds on the same principles, but with a little twist. This time we're looking for combinations of k numbers from a set of n numbers.
Okay.
So the code introduces this thing called a path variable to keep track of the numbers that are currently in the combination.
So as we explore deeper, we add numbers to this path.
Exactly. And if the length of the path hits k, boom, we've got a valid combination.
And if it's too short or too long?
Backtrack and try other numbers.
This whole path concept is really interesting. It's like leaving breadcrumbs in the maze so you can retrace your steps if you hit a dead end. Now, what if we have, like, duplicates in our set?
Ah, yes.
Like in problem 90, finding subsets with duplicates.
That's where things can get a little trickier. If you just apply the same logic, you'll end up with duplicate subsets.
Oh, right, because we don't want to count the same subset multiple times.
Exactly. So the code includes this very clever condition within the DFSauce function.
What does it do?
It checks if the current number is a duplicate of the previous one, and it only includes it if it's the first occurrence in the subset. It's like if you encounter the same door twice in a row in our maze analogy, you only need to open it once.
That makes a lot of sense. Each subset remains unique, so we're not just exploring every path, we're being smart about which paths we take.
Yeah. And that idea of pruning unnecessary paths is a really powerful concept in computer science.
So we're not wasting time exploring paths that lead to dead ends.
Exactly. It helps us make algorithms more efficient.
I see. I'm starting to see how these seemingly simple ideas can have a big impact on solving these complex problems.
Now imagine you're given a set of numbers and a target sum, and you need to find all the combinations that add up to that target.
Okay.
These are called the combination sum problems, like 39 and 40.
So it's like having a bunch of ingredients and trying to find all the residues that add up to a specific calorie count.
Exactly. The main difference between problems 79 and 40 is whether you can repeat numbers in a combination.
So in one, you can reuse ingredients, and in the other, you can't.
Exactly. Problem 39 allows repetition, while 40 requires unique combinations.
Got it. So how does the code adjust for these two different scenarios?
Well, both problems use this variable called pathSum to keep track of the sum of the numbers in the current path. If pathSum equals the target sum, boom, you've found a valid combination.
Okay.
But problem 40 needs to make sure that it's not counting any duplicates.
Right.
So it has an extra check to see if the current number is the same as the previous one and if the previous one was already used.
We're back to being smart about printing the search space.
Exactly. We want to avoid those redundant calculations.
This is really fascinating. Now imagine those old school phones with letters on each number key. Could you list every possible word you could type with a given number?
Oh, man. I think I'd need some help with that one.
Yeah, it sounds like it could get out of hand pretty quickly.
It definitely could. That's where DFS comes in. It's like having a super fast typist that can try every possible letter combination.
So it's like DFS is traversing this tree of choices with each branch representing a different letter.
Precisely. The code uses a map to link each digit with its letters, and then that DFS function systematically explores each letter combination.
And when the length of the current combination equals the length of the phone number, you know you've got a valid word.
Exactly.
Okay, we've gone from finding subsets to generating letter combinations.
All thanks to the power of DFS.
This is making me think about other ways we can arrange things. What about problems that involve finding all possible orderings of elements, like permutations, problems 46 and 47?
Permutations are a really interesting use of DFS.
Yeah.
In problem 46, we're dealing with distinct integers. So the code uses a used array to keep track of which numbers have already been included in the permutation.
So if a number is marked as used, we skip it to avoid repetition. But what about problem 47, where we might have duplicate numbers? How do we avoid getting the same permutation multiple times?
In problem 47, the code actually sorts the input numbers first.
Oh.
This makes sure that any duplicate numbers are next to each other. Then if the current number is a duplicate of the previous one and the previous one hasn't been used yet, the algorithm skips the current number.
So by sorting and checking if the previous duplicate has been used, we prevent those unnecessary calculations. Each permutation stays unique.
Precisely. It's a small tweak that makes a big difference.
It's mind-blowing. DFS really is a problem-solving chameleon. We've covered finding combinations, generating letter combinations, and even working with permutations. But it feels like we've only just scratched the surface. What about something more complex, like a binary tree?
That's a great question. And that's exactly what we'll be diving into in the next part of our deep dive.
Awesome. See you soon for part 2, fellow explorers. Welcome back, deep divers.
Ready to climb some trees?
You bet. We're about to journey into the heart of tree structures.
Still guided by our trusty DFS algorithm, of course.
Of course. We're shifting gears a bit.
Yeah, from like linear structures to something a little more branching.
And just like we explored every path in that maze analogy earlier, DFS can help us navigate every nook and cranny of a tree. In fact, problem 113 in our notes is all about finding paths in a binary tree.
Paths that add up to a specific target value.
It's like finding the perfect combination of branches that lead to like a hidden treasure or something.
That's a great analogy. The code for problem 113 basically recursively explores the tree, adding the current node's value to that path sum and keeping track of the nodes in a list called path.
So at each node, it's like the algorithm has to make a decision, go left or go right.
It's like choosing which fork in the road to take on our treasure hunt.
And if it reaches a leaf node, the end of a branch, and the path sum equals the target sum, we know we found a valid path.
Exactly.
It's really amazing how this algorithm can adapt to such different structures. I mean, we've gone from linear lists to branching trees.
It's all based on the same fundamental principle, though.
This is making me think about all sorts of real-world applications. Could DFS be used to, like, map out relationships in a family tree? Or even analyze connections in a social network?
Oh, absolutely. DFS is actually really widely used in social network analysis to identify communities and suggest connections. It's like a digital anthropologist.
Wow. But speaking of intricate webs, what about something like a word search puzzle? Could DFS help us find a hidden word in a grid of letters?
You know it can. Problem 79 in our notes actually tackles that very problem.
Okay.
The code explores all possible paths in the grid. starting from each cell and moving in 4 directions. Up, down, left, right.
So it's like a tiny explorer, checking every possible path, looking for that specific sequence of letters.
And to prevent it from getting stuck in a loop, it uses a visited set to keep track of the cells that have already been explored.
So it doesn't keep going back and forth.
Right.
This is making me think about how DFS could be used in image processing.
Oh, interesting.
Imagine an image made up of pixels. Could you use DFS to identify connected regions of the same color? Like to identify objects in a photo?
You're totally right. That's actually how the flood-fill algorithm works, which we can see in problem 733. It uses DFS to recursively explore connected pixels and basically fill them in with a new color.
So we're giving DFS a digital paintbrush and letting it color in all the connected areas?
Exactly.
This is incredible. We've gone from finding treasure in trees to exploring word search puzzles to even coloring images, all with DFS.
DFS is a pretty versatile tool.
It is, but even the most reliable tools have their limitations, right?
That's true. No tool is perfect for every job.
So what are some of the things we need to be aware of when we're using DFS? What are some of those limitations?
Well, one thing to keep in mind is that DFS isn't always the best choice for finding the shortest path.
Right, it's like taking the scenic route. You might find all the hidden rooms, but it might not be the most efficient way to get to your destination.
Exactly. If you need to find the shortest path, BFS or breadth first search might be a better choice.
So it's like choosing between a leisurely exploration with DFS or a direct targeted approach with BFS.
Yeah.
It depends on what you're trying to achieve.
Now, another thing to be really cautious of is the potential for infinite loops, especially if the graph or tree that you're exploring has cycles.
Right, like going around in circles. Back in our maze, we have to be careful about that.
Yeah, you need to make sure your code has cycle detection to prevent that from happening.
Okay, so even though DFS is super powerful, we need to be mindful of those limitations.
And choose the right tool for the job.
Are there any ways to make DFS even more powerful?
Absolutely. There are a few variations of DFS that can help with that. For instance, backtracking is essentially DFS with an added constraint satisfaction. At each step, the algorithm checks if the current partial solution meets the problem's requirements.
So it's like having a checklist along the way to make sure you're on the right track.
Exactly. If the current path satisfies the constraints, you keep exploring. If not, backtrack and try a different path.
It's like having a built-in safety net to make sure you're only exploring valid solutions. I can see how backtracking would be really useful for solving puzzles.
Like Sudoku.
Yeah, or even planning a trip.
Now, another interesting variation is called IDDFS.
IDDFS.
It stands for Iterative Deepening Depth First Search. It's like combining the best of both worlds, the space efficiency of DFS with the completeness of BFS.
Oh, that sounds interesting. So how does that actually work?
Imagine you're exploring a library, right? Instead of going down one aisle until you reach the end, you systematically explore each bookshelf on the first floor, then move up to the second floor and explore each bookshelf there, and so on.
So you're exploring in layers, but using DFS to thoroughly explore each layer.
Exactly. This way, you can find the solution without using too much memory, which can be a problem when you're dealing with very large search spaces.
Wow. So DFS is like this versatile toolbox with different tools for different situations?
Exactly. And with the right tools and a good understanding of their strengths and limitations, you can tackle almost any challenge.
This deep dive has been so eye-opening. I feel like I've unlocked a whole new way of thinking. It's more than just an algorithm. It's like a whole way of thinking about problems.
I couldn't agree more. And as we wrap up part 2, I want to encourage everyone to think about how you might apply these concepts in your own work or even in your everyday life.
Great idea. Join us for part 3, where we'll put all of this together and explore some final, thought-provoking questions. Welcome back, explorers. Our journey with depth-first search has taken us through mazes, up trees, and even into the world of digital art.
It really has been quite the adventure.
We've seen just how versatile DFS can be, solving all kinds of problems, from simple combinations and permutations to navigating complex structures like those trees and grids.
It's amazing how much you can do with just one algorithm.
But before we wrap up our deep dive, I think it's a good idea to take a minute to reflect on everything we've learned.
Yeah, good idea.
What are some of the key takeaways that you think our listeners should remember from all of this?
Well, I'd say the most important thing to understand is that core idea behind DFS.
You mean that deep, systematic exploration?
Exactly. It's about carefully examining every single possibility.
It's like being a detective, right?
Yeah.
Examining every clue before moving on to the next.
Exactly. And we saw how that approach can be used in so many different scenarios.
From those letter combinations on a phone,
Yeah.
all the way to finding those connections in a social network.
Yeah. It's powerful stuff.
And it's not just about blindly exploring every path, though.
No.
We have to be clever about how we write our code,
Right.
how we set up those functions and make sure we've got those exit conditions to avoid those infinite loops.
Absolutely. Remember those 3 questions we talked about?
Defining the function, breaking it down recursively, and setting up that exit condition.
Yeah, those are crucial for making DFS work.
And of course, we can't forget about the potential downsides, like how DFS can get stuck in those cycles,
Oh yeah, those can be tricky.
or how it might not be so great when you're trying to find the absolute shortest path.
Right, you got to be aware of the limitations of any tool, even a powerful one like DFS. Sometimes another algorithm like BFS might be a better fit.
But even with those limitations, we learned that we can make DFS even better
Yeah,
with techniques like backtracking and iterative deepening.
those give us more flexibility and control.
It's like having a bunch of different tools in our DFS toolbox.
Exactly.
This deep dive has really been amazing. I feel like we've uncovered a whole new way to approach problem solving. It's more than just code, it's a whole way of thinking.
I completely agree. It's really exciting to see how these concepts can be applied in so many different areas.
And speaking of exciting, I have a final question for our listeners.
Okay, what is it?
We've seen how great DFS is at exploring all those possibilities. But what if we need to find a solution really quickly, even if it's not the absolute best one? Could we somehow, guide DFS to prioritize certain paths over others? Maybe using some kind of estimation or heuristic?
That's a great question. It's like giving our explorer a compass, right, to point them in the right direction.
Exactly.
It would definitely make things more efficient. But it also introduces a new challenge, figuring out how to design those heuristics effectively.
It's definitely something to think about, a challenge for our listeners to explore.
Absolutely. See what you can come up with. Maybe there's some clever ways to combine these ideas.
And on that note, I want to say a huge thank you to all of our listeners for joining us on this incredible deep dive into depth-first search.
We hope you enjoyed the journey as much as we did.
We hope you feel inspired to tackle some of your own algorithmic adventures. Until next time, keep exploring.
And keep those algorithms running.